Hello everyone, I'm Ragini Nikumbh and I'm a PhD candidate at Kansas State University working under the guidance of Dr. Christopher Jones. So today I'll be discussing the effect of admixture types on the durability properties of high strength concrete. So the overview of the presentation is given on screen. So according to the ASC 2021 infrastructure report, about 43% of public roadways in the United States are in poor or mediocre condition, and about $53 billion are needed to annually rehabilitate the pavement and perform other functional operations. So ideally, we believe that like in perfect conditions, concrete has this immeasurable service life, but that's not the case on field. There are multiple tensile or mechanical factors which play a role, out of which the freeze-thaw cycles, de-icing salt, and shrinkage are one of the factors that kind of deteriorate the concrete pavements. So for this purpose, the Kansas Department of Transportation supported this research where uh, like the where the deteriorated concrete pavement was replaced to increase the overall lifespan of the concrete pavement. But even after that, there was still damage observed in the concrete pavement. And one of the three type of failures was observed. One was a cracking in the repair material, the other one was cracking in the substrate concrete, and the third one was cracking at the bond interface. So this research focuses on the type 1, which was the cracking in the repair material. So initially, it was thought that the main reason for this failure was that since high strength concrete is composed of high cement content and low water to cement ratio, this might have caused this damage. But uh, this might have caused the damage since low water to cement ratio lowers the workability, and that's why higher dosage of chemical admixtures are required. While for high cement content, a higher shrinkage is observed due to self-desiccation of concrete. This was due to the high heat of hydration that is associated with the high cement content. And this causes cracking and shrinkage at an early stage, which leads to which gives way to other deterioration, uh, which is the freeze-thaw effect, and freeze-thaw effect does inadequate frost durability or inadequate porosity or permeability is observed in these pavements. So for this purpose, the first part of this project focus on understanding how much is the minimum cement or what is the cement content which will cause the inadequate frost durability. That's why the research by Dr. Yadira Porez and Faisal Qadri focused on understanding if different cement contents have if different cement content with different cement content, can we still reach the minimum strength requirement? That's why Dr. Yadira Porez focused on using low cement content standard and high cement content. And it was observed that all of them were able to satisfy the minimum strength requirement which was given by KDOT, but they all still had inadequate frost durability. That's why the current research used the minimum cement content, which was 564 pounds per yard cube, and we focused on understanding the effect of admixtures that are used by the effect of admixtures that are used in the concrete mix design. And the HESC mixtures were developed in accordance with the KDOT specification, which is they had to reach a minimum strength of either a minimum compressive strength of either 1800 psi or a tensile strength of at least 380 psi. And they had the fresh concrete properties, which were again recommended by KDOT. So the HESC mixers, they were tested for compressive strength, drying and autogenous shrinkage, and their freeze-thaw resistance. So the materials that were used were type 3 Portland cement, as I mentioned before, of low content, 564 pounds per yard cube. 50% fine and 50% coarse aggregate was used. The limestone aggregates were used in order to make sure that the damage or the inadequate durability of the concrete mixtures is not due to poor aggregate quality. 2% calcium chloride was used, and in addition to simply testing the HESC mixtures with different admixtures, we also use internal curing to see whether that has an effect in whether that reduces the shrinkage that is observed in the HESC mixtures. A water to cement ratio of 0.37 was used, and an air content of 6.5 plus minus 1.5 was targeted. So there were three type of admixture combinations which were used. These three are like the most popular admixtures that are currently used on field, and the combination of admixtures was recommended by the admixture companies. So as you can see, the HESC1 is one of the old technologies. It is a mid-range water reducer, and it's a Windsor resin. While the other two, those are high-range water reducers, and those were kind of like the new technologies in market. So the fresh concrete properties for all the six mixtures were within the targeted range, and as you can see, they were all able to achieve like the minimum concrete compressive strength. Although the samples with the internal curing achieved a slightly lower compressive strength than those without the internal curing, and to make sure that they achieve like the minimum requirement of like 1800 psi within 6 hours. You can see it on board that they all achieved the minimum requirement of 1800 psi within the 6 hours. Okay. The autogenous shrinkage for all these samples have been shown on screen. We can see that the samples with the internal curing, those had like a high initial shrinkage, but after that the shrinkage remained constant. On the other hand, the mixtures that were prepared without the internal curing, as you can see, like they had this small initial shrinkage, but after that they showed a large drop in the shrinkage values. And the shrinkage over a long period of time, which was recorded as the drying shrinkage, is shown on screen. We can see that the internal curing was able to give us lower shrinkage as compared to those without the internal curing. And although all of these mixtures had the same mix design, the same materials, and everything was same, yet they showed completely different results. And the main part, which was the freeze-thaw resistance. So as we can see, the freeze-thaw resistance was calculated by running the samples until they broke down in the freeze-thaw chambers. About 6 to 8 freeze-thaw cycles were conducted every day, and we can see that the samples with the HESC3 admixture combination, those showed the least freeze-thaw resistance as compared to the samples with the HESC1 admixture combination. And based on the RDME, we can see that the drop in the RDME for HESC3 sample was quite fast as compared, followed by HESC2 and then by HESC1. We had to remove HESC1 after about 900 cycles because the RDME remained constant, and and since the KTMR has it requires only 600 cycles, so we thought we should stop the experiment over there. So as we can see, even if you have the proper mix design, you have the perfect or the fresh concrete properties within the given recommendations. Still, if the admixture combination or if the admixture combination is not proper, or if it is not giving you a stable entrained air void structure, we will have poor freeze-thaw durability, poor freeze-thaw resistance. So to conclude, we observed that the minimum strength specification as per KDOT section 833 was satisfied by all the HESC mixtures, although the HESC mixtures with the internal curing showed a slightly lower strength than those without the internal curing. On the other hand, the durability properties of all the HESC mixtures were quite different from one another, even though they had the same mix design, same materials, and everything. The HESC one admixture combination with the internal curing was one with the highest freeze-thaw resistance, while the HESC admixture combination number 3 showed the least durability properties. And as I said before, even though they had the proper fresh total air content, it was insufficient to ascertain the freeze-thaw resistance. We commonly believe that if we strike that total that like minimum total air content, we will have proper freeze-thaw resistance, but that's not the case. That's why currently we are waiting for the petrographic analysis of these samples, which will give us a better idea on how the admixture combination, on what role the admixture combination played on the entrained air void structure. And apart from that, we are also studying in addition to type 3 cement, if the admixture compatibility plays a major role in other type of cements. We would like to thank KDOT and Monad Cement Company and also ACI for giving us the opportunity to present the research.